Hello and welcome to our next set of stats notes. We're doing section 8.3, which is our last section of chapter 8, which means they're also almost done with the notes for our second unit exam. Our second exam covers chapters 6 through 8, so this is the last set of notes will be on this next exam. You should be getting ready for that exam. It's coming up here soon. Make sure you're going through and doing the practice exam. Make sure you finished all the homework and the quizzes. If you had a bad grade on quiz, you should probably retry that as a good practice for the exam. So just make sure you get ready. Remember, you get a 3x5 note card for that exam. So any kind of formulas or calculator like inputs you want to write down, you can run that formula on the 3x5 note card and bring with you to the exam. So that's coming up. Just a heads up. Now this next section is going to be a lot like 8.2. We're just going to do some hypothesis tests. This case, though, we are going to be doing tests about population mean versus 8.2, which was about proportion. Remember that with mean, we typically don't know sigma, the standard deviation for the whole population. And because we don't know that, we end up having to estimate with sample standard deviation, or S. And because of that estimation, we end up having to work with t-scores. So that's one of the big differences you'll see between the population mean versus the population proportion, is we are going to be working with t-scores. So when you're working with your calculating t-scores, remember we'll use this formula. So that's going to be our formula for the t-scores in this section. We'll see though that we use technology. We don't really end up using this formula that much. I think you kind of saw that already a little bit, but we'll see that we don't really use this formula because the technology kind of does that for us. Now one note, some of you are like the tables, and that's fine. You can use the tables for this, but when doing this section, the tables can make life a little harder. So when you're trying to find your p-value, when you're doing the p-value method for hypothesis testing, you don't usually get a really specific good value because the table isn't big enough. If you had a lot bigger table, a lot more entries, if you get better values, but because our table doesn't have enough entries, you're going to have to kind of almost approximate. But it is enough to give you a final answer. So you can still use it. So we're going to show an example down here. And this example is going to show how using the table can make life a little bit harder. So if we're going to use the t-distribution table, we're going to find the p-value for a left-tailed one mean t-test with a size of 18. So that's your sample size. And the t-score they got from their test statistic is going to be this negative 1.645. And we're going to try and determine if we should reject at the 5% significance level. So they gave us the sample size, which is n, is 18. Remember that when you're doing t-scores, you need the degrees of freedom, and the degrees of freedom is always one less than the sample size, so that'd be 17. They gave us the significance level, and they gave us the t-score. So we're going to go to the table, and we're going to try and look up this negative 1.645, and then we want to compare it with the 5% level, right? Because the p-value, we're going to always check the p-value versus the significance level. So we'll check this p-value next to the significance level of 0.05 and see if it's small enough, right? So if I go onto the table, since we're doing degrees of freedom are 17, we'll go to the 17 here, and then we're looking for 1.645 because we're trying to go backwards and finding the area. So 17 negative 1.645, you'll notice, is not on here, right? 1.645 is not on here. And this is what I was talking about. You can't really get an exact value because 1.645 is not listed. This doesn't have enough rows. But what you can do is you can note that 1.645 is right here between the 1.74 and the 1.33, which means that for degrees of freedom 17, that 1.645 would have an area somewhere between 5 and 10 for one tail. So we don't know what it is, but we do know that the p-value is bigger than 0.05 and less than 0.10, 0.10. So we don't know what the value is going to be. We just know that it's going to be between those two numbers. Well, that's actually enough because we know that the p-value is going to be bigger than 0.05, which is our significance level. So we don't know what it is, but we do know it's bigger than 0.05, which means for us, since it's too big, it's bigger than 0.05, we fail to reject. So if you're using the table, you can use the table. You're not going to get a specific p-value. So if like a homework question or a quiz question asked what is the p-value, the table's not going to give it to you. It's not going to be accurate enough, but it will let you figure out whether or not to reject or fail to reject. So you can do that. Now if you use technology, this whole problem doesn't happen. So if you're just like me and you prefer to use the calculator, That's fine. You won't have to worry about this at all. This is just something that pops up if you use the table. Again, this was a left-tailed test. That's why we had negative value here. But these are all positive on here because it doesn't have a negative side. So we just turned it into a positive and looked at that value. Again, we just looked for the value between those two numbers, and that kind of gave us an idea of what the area was. Since we're doing one tail, right, because it's a left-tailed test, one tail, that's why we said it was between those two numbers. Okay, let's move on. That's all we have to worry about with the table. The rest of this, like I said, we could just use the calculator, and that's what I'm going to do from here on out. Okay, so just like last time, let's have a kind of a breakdown of what we would do to perform the test. Just like always, when you're going to do a hypothesis test, first thing you're going to do is state the null alternative. You figure out what the significance level is. That's given pretty much always. Select which method. Are you going to do critical value, p-value, or constant interval? And again, if you're just trying to do the test, any one of those work, but sometimes they might ask you for critical values, or they might ask you for the constant interval. And so then you might need to use those things to get that. We'll do our test, and then we'll decide whether to reject or fail to reject. If you're doing the critical value method, first we need to find that test statistic, and then find the critical values. Remember, the critical values come from the significance level. That's where we get the critical values. Then we compare the test statistic with the critical values, determine if the test statistic is in the critical value. Remember, it's in the critical region or the rejection region if it's extreme enough. So is it extreme? If it's really extreme, it's really far left or right, whichever direction you're going, then you get to reject, and you can reject the null. We have the p-value method. Again, the p-value method, we still have to find that test statistic because we use the test statistic to get our p-value. The p-value is the probability of getting a value beyond that test statistic. And if the p-value is small, remember if the chances are small, then smaller than the significance level, that's when we reject. If it's smaller, then we reject. So again, we get the p-value from the test statistic. And then there's the third method. If you want to do the other method, or if they ask you to, you can do the confidence interval method, where you calculate the confidence interval. The big thing with the confidence interval you saw last time is you need to figure out what the confidence level is. It's based on the significance level, and it's based on how many tails there are. So you have to be careful about that. Once you build the confidence interval, check the claimed value. In this case, it'll be a mean, right? Because now we're doing means, and see if that's not in the confidence interval. If it's not in there, that's when you fail. So if it's not in, then we fail. Okay, so let's do that. We're going to do this test, the given information. So they tell us we want to do it at a 5% level, so that's our alpha, right? Alpha is 5%. They give us a sample mean, so that's the average from our sample. The sample standard deviation, so that's the spread of our sample. Sample size, 28. The null hypothesis is that the mean is equal to 25. The alternative hypothesis is the mean is less than 25. So we saw before that we could calculate the values by hand, but it was easier to use the calculator. And the same thing could be true here. Because we're doing means, we're going to be doing a t-test, not a z-test. So we're going to go into the calculator. First off, let's just run the t-test and see what that gives us. I go to my calculator and I hit stat and go to tests. And there's the t-test is actually just the second option. So I'm going to do a t-test. I'm going to use stats because that's what they're giving us. They didn't give us the data. They didn't give us the actual values. They just give us like the summary data, the information, the statistics of the mean, the sample standard deviation, that kind of stuff. So we're going to use the stats. The claim value is going to be 25, right? That's the mean that they are proposing the claim. So we're going to put 25 in for the claim value. The sample mean is 22. The sample standard deviation is 8. The sample size is 28. And we're doing a less than test, right? We're doing a less than. So we're going to make sure the less than is highlighted, hit enter on that, and calculate. And what this gives us, the t-test, it gives us first a t-value, which is going to be your test statistic. So the test statistic for this one is that. Then it's going to get a p number, which is the p-value. 0.0287 is the p-value. And then it's going to give you the sample mean and the sample standard deviation and sample size, which are all stuff we already had. So really that's just a check to make sure you type those in right. If any of these numbers come out wrong, it's like, oh, well, I typed those in, so I messed them up, right? So you don't really need these three. You really just need the first two values. That's what we want. Got the test statistic, got the p-value. Now if I'm going to do critical value method, right? Critical value, or with the critical value, we need to figure out what the critical values are. So I'm going to draw my little distribution. Think about the fact that we're doing a less than test. So this would be a left-tailed test right there. Critical values want to have that percent in this region. So I want this to be a 0.05 region. And find out what the critical value, what z-score gives me that. So to do this, because this is a t-test now, right? I shouldn't put t, I should put z, I should put t. That was a bad, I was just doing the other set of notes, and so I was thinking z's. We're doing t-test, it should be a t. We're going to do the inverse t, because we're trying to find the t-score based on that area. And we'll put in our 0.05 for our area, and then we want the degrees of freedom. In this case, since there's 28 sampled, subtract 1, and your degrees of freedom will be 27. So my 27 is going to be my degrees of freedom. I'm going to do second distribution, inverse t. Area is 0.05, 5% to the left. Degrees of freedom is 27. Put that in. And that gives me the t-score we want, which is going to be negative 1.703. Okay, so now we got the critical value to compare with our test statistic, and we say, is the test statistic extreme enough? So if I compare the test statistic with the critical value, the test statistic is at negative 1.984, and it is even smaller than the negative 1.703. So in this case, because the test statistic is way out here in this region, that's where the test statistic is, it's way out here, and here, 1.9. We end up rejecting. We're in the rejection region. So this one we reject the null. So using the critical value method, yeah, we do reject. Now what about if I use the p-value method? P-value, remember you just compare the p-value with the significance level. So that's all we have to do for p-value. So for the p-value approach, for the p-value with the significance level, alpha, p-value is 0.0287, significance level is 0.05. Well, 0.0287 is less than 0.05. Remember, if the p-value is small, if p is low, null must go. So we reject the null. So that method still lets us reject. Last method, if I want to do the confidence interval method, note that we're doing a one-tailed test. So if I draw my confidence interval, I need to have 0.05 in this tail. Well, to make sure the tails match, this tail also has to be 0.05. So in the middle here, I'm going to actually have 90% or 0.90, except 5% in each tail. So to do this confidence interval, we're going to do the t interval. We're going to do it with a 90%. So I'm going to go to my second distribution. Inverse t. Or no, I want a t interval. That's on tests. That's why I'm not finding it. I went to the wrong one. I want t interval. And then we'll have our mean, which is 22, sample state deviation, which is 8, sample size, which is 28, and the confidence interval, this is going to be 0.9. That's where we're going to put that 0.9 in. And then calculate, and we get an interval from 19.425. 19.425 to 24.575. So that's our confidence interval. Again, with the confidence interval, we check to see if the claimed amount fits in there. So the claimed amount is 25, which does not fit. So does not contain the mean of 25. So we reject. Which again, that's we should do the same thing on these. With these ones, with the mean tests, the confidence interval method will always give you the same result as the other two methods. We saw with the proportion, and I said that with the proportion, that's not always true, but with the means, when you're doing means, then all three tests should always give you the same result. So as far as determining whether or not to reject or fail to reject, it really doesn't matter which test you do with this method, with the means. Again, I'm just showing all three because they might ask you for the confidence interval. They might ask you for the critical value. So you should know how to find those. But you can pick which method you want to do the problem. Okay, we're going to do this a couple more times, but that's really what this section is just doing hypothesis tests for means. Now, just like before, we do have some requirements. With proportions, we saw the requirements about having 5 successes, 5 failures. With the means, the requirement was having a big enough sample. So we had to have a simple random sample, and then a big enough sample. It either is normally distributed or bigger than 30. It could be both, and that's fine, but it had to be one of the two. In fact, our last problem, I only had a sample size of 28. So unless the data was normal, we wouldn't actually be able to do this hypothesis test. So I'm going to assume at this point that the data was normal, and that's why you're allowed to do it. This next one, let's see what it says. So it says the study claims the average team plays 4.4 hours of games per week. So that's their claim, is the average of 4.45. If the distribution play time is normally distributed, so that the data is normally distributed, which gives us that one, which means yes, the requirements are met. So as soon as we know the data is normal, we can say, okay, we don't have to worry about anything. Even if it's a small set of data, you're still allowed to go. We want to do a t-test at the 5% significance level, so that's our significance level, with simple random sample of 15 people, that's going to be a sample size, and from the sample they got a sample mean and a sample standard deviation. So this guy would be sample size, this would be our claimed value. So our null hypothesis would be that the mean is equal to 4.45 hours. That's your null hypothesis. Alternative hypothesis would be that the mean, in this case, well, does it tell us that more than or less than? Claims that the average team plays 4.45 hours. Nowhere does it indicate they're looking for less than or more than. So in this one, we'll do not equal to. Usually if they say something about testing whether it's more or testing whether it's less, then we use one of those. But there's nothing saying that here, so we're just going to test if it is equal to or not equal to 4.45. Okay, so again, we'll do the t-test, because that'll give us a lot of good information, like the p-value and the test statistic. So we'll do that first. So stats, tests, t-test. And what's the statistics? The claimed value is 4.45, so we'll put that in for the claimed value. The sample mean is 3.935. Sample standard deviation is 1.025. Sample size is only 15, there's only 50 people. And this one, we're doing a not equal to test. We're going to put not equal to. Okay, once you get all that in, we're going to calculate, hit calculate, and there it gives us the information. So it tells us, the t-score, the test statistic, is negative 1.9459, and the p-value is 0.0720. And then the other stuff, the sample mean, sample standard deviation, and the sample size, that's all stuff we already know, so I'm not going to write that down. So that comes from there, and then we can start thinking about the critical value method. So if I want to do critical values, I'm going to think about my distribution. This one's going to be two-tailed, right, because I'm splitting up this, saying not equal to, so I have two tails. And the significance level, the 5% significance, is split between the two tails. So I'm going to put 0.025 in both tails. 0.025, which is 2.5%. That way I get my 5% split up between the two. So I'm looking for the negative t-score and the positive t-score that would give me that. So I'm going to do inverse t at that 0.025. And because this is sample size of 15 people, my degrees of freedom would be 14, right? Degrees of freedom is always one less. So that's what I'm going to put in there. So we're going to do our distribution, inverse t, area 0.025, because 2.5% each side. Sample size was 15, so we have 14 for our degrees of freedom. And now we have our t-score. So our t-score should be negative 2.145. Again, that's the left value, right? So it's negative 2.145 is the left value. Positive 2.145 would be the right value. So we're looking for our test statistic to be more extreme like that than to be further out. But in this case, the test statistic, this t, is actually about here, 1.9. So it's not extreme enough, and so in this case we would fail to reject. So using the critical value method, we see we're going to fail to reject because the negative 1.9 is not further out than our critical value. We're always comparing the test statistic with the critical values. If it's not more extreme, then we fail to reject. Okay, if I want to use the p-value method, nice thing with that is all you have to do is compare the p-value with the significance level, 5%. And that's it. So I'm just going to take my p-value, my significance level alpha, and compare them. So I get 0.0720, and I get this one as 0.05 for my alpha. And since 0.07 is too big, it's bigger than 0.05, we fail to reject. Same result. The last thing I need, what I want to do is when we do my confidence interval method. The confidence interval, I always got to think about what's my confidence interval going to look like. So here, I'm going to have that 5%, but split between the two because it's a two-tailed test. So I'm actually still going to have 0.025 in both tails because that's what matching there, 0.025. So when it's a two-tailed test, remember you just do 1 minus alpha. And so the middle region, take away 5%, you're left with 95%. So we're going to be doing a 95% confidence interval. So I'm going to do T interval. And my confidence interval is going to be a 95% confidence interval. So let's do that one. Second, or no, stats, T interval. So my mean they gave us is the 3.935, sample standard deviation is 1.025, sample size 15, confidence level is 0.95, and so my T interval is going to be 3.3674 and 4.5026. And as always, we're going to check that. We're going to say, does the claimed value, which in this case is 4.45, does it fit in there? So it does. It contains the claimed mean of 4.45, which means we fail to reject. Because again, if it contains that, we can't say it's bad. It fits. So since that fits our result, we're not going to be able to reject it. So we fail to reject. Okay. So again, all three methods give us the same result. And that's something you'll see with this, with the means. All the different methods always give you the same result. So you don't have to worry about which one you do versus being accurate, but you just have to know how to find critical values or confidence intervals for the homework or for the test. Or like that. One more. Note, sometimes the data values will be provided without the summary statistics. So if you're doing a problem and they say, here's the data, and they don't give you the statistics, the mean, the sample standard deviation, that stuff, don't forget, you can always take that, you can always enter that data into list one, and then just use the one bar stats, and that will give you your sample mean and your sample standard deviation. So if you ever get a problem, they do that, just use the one bar stats, and then you got your sample mean and your sample standard deviation. You don't have to worry about it if they give you the data, because you can get that same information. Also, if you need to check normality, you can always use the normal quantile plot. So normality we saw earlier. You just graph it in the normal quantile plot, and that'll check your normality, because you can look for that straight line. All right, last one. Let's do one more. National Weather Service reports the average length of a tornado's damage path is more than 2.55 miles, so we're looking at more than 2.55 miles. In a study of 500 tornadoes, that's their sample size. The mean length, so the average length of the sample, is 2.62, and the standard deviation of 0.7956. We want to test the claim using 5% significance level. So in this case, the null would be that the average length is 2.55 miles. And the alternative, well, now they're looking at more than, right? So they want to say that it's more than, they're thinking greater than, so we're going to say that the mean is greater than 2.55. Okay, they did a sample of 500 tornadoes, so that's their sample size. They have their sample mean with X bar, sample standard deviation, which is S, and their significance level alpha. So first off, we're going to do that T test, because again, when we're working with means and sample means, we're going to be doing T tests. Put in the data for the T test. So I'm going to hit stats, test, T test. We're doing stats. The claimed value is 2.55. The sample mean is 2.62. The sample standard deviation is 0.7956. The sample size is 500. They had a lot of tornadoes they tested. And then we're doing a greater than test because we're saying we're looking for more than 2.55 miles. Okay, calculate that and see what we get. We get a test statistic T of 1.967. We get a p-value P, 0.0248. And then again, the rest of the stuff is stuff that we already know. That's what we put in, just making sure we typed it correctly. I want to do critical value method. Think about my distribution. Since I'm doing a more than, I'm just going to have one tail. This tail needs to have the 5% significance, so 0.05 in this tail. We're looking for the t-score that does that. So again, we're going to do inverse t with that 0.05 is what we want in that tail. And then because the sample size is 500, the degrees of freedom would be 499. This is one you couldn't even do on the table. So if you're using table, you'd be stuck on this one because 49 is way off the table. This is one of the reasons why the calculator is a little bit better, because it adapts to things like really big sample sizes. Okay, stat, tests. Oh, I want to do second distribution, sorry. Inverse t is under the second distribution. So inverse t, or 0.05 for my area, and 499 for my degrees of freedom. And we get negative 1.648. Again, this is giving us the t-score for over here because I didn't flop it around. So this is actually positive 1.648. We do that a lot, where we just calculate the one that would be over here and then just switch it to positive. Okay, so we get 1.648. That's what we compare with our test statistic. So again, our test statistic we got using the calculator. Now we just found the critical value. We always compare those. In this case, the test statistic of 1.967 is bigger than the critical value of 1.648. And since the test statistic is bigger, it basically tells us that this value is going to be way over here. 1.967 is going to be in the critical region, and so we would reject the null. So their claim that it is equal to 2.55 will reject, or sorry, that null hypothesis and go with the alternative, which is their claim. That's for them. We'd support them in this case. So in this case, we'd support their claim. They said, hey, it's more than 2.55 miles. And we went and tested that and said, yeah, we reject the null of equality, and we support your claim, your alternative claim, that yes, it is bigger than 2.55. Next one, p-value. Again, p-value is pretty straightforward. Just compare significance level with p-value. So I'm just going to do p-value, say the 0.0248. How does that compare with the significance level of 0.05? Well, it's smaller, right? If the p-value is small, then the null must go, right? P is low, null must go, so reject the null. Anytime the p-value 0.02 is less than 0.05, reject the null. So same conclusion. And then confidence interval, if we want to do a confidence interval. Because this is a one-tailed test, so they have just the one tail has all 5% of your data. To make a confidence interval, we need to have a matching tail over here that also has 0.05, so 0.05 on both sides. So if I take 5% off both sides, I'm going to be left with 90% in the middle. So we're going to do a confidence interval with a 0.90 confidence level. So again, this would be 1 minus 2 alpha because it's a one-tailed. So anytime you have a one-tailed test, you got to worry about that 0.05 being both tails, so you'll leave just the 90% in the middle. Okay, let's do that. We're going to do the t interval. So I'm going to stat, tests, t interval. Because it's the 2.62, which is our sample mean. We already got that. Sample standard deviation, 0.79656. Put that in. Sample size of 500, but the confidence level should be 0.90. Okay, so that's usually all you have to change the confidence level. The other stuff we already put in. Unless you're doing this one first, I guess, then you have to do it differently. So here we have 2.5614 to 2.6786. That is their confidence interval. So it's only that far apart. And since the number that we claimed is 2.55, that's our number we claimed, 2.55, which is below, right, out of there. So it does not contain the mean of 2.55. Then we reject the null because we say, oh, well, they said it was the equal says it's 2.55. That's not even in my interval, so I don't accept it. So we're going to say it's actually larger. So this interval is actually above the 2.55. It is larger. So we're going to reject the null, and again, we're going to support their claim. We're going to say, yeah, it is greater like you said it was. It's not equal to. Okay, so that's it for hypothesis testing. Now I say that, but that's really kind of a lie because we'll find out that most of Unit 3 is more hypothesis tests. But what we've done here is in Chapter 7 and 8, we've introduced the basics of confidence intervals and the basics of hypothesis tests. So in Unit 3, in our last part of this class, we're going to basically look at specific uses, times when you might have more than one population, when you might be testing slightly different things. And so we'll be doing a lot of hypothesis testing, but in a little more complicated situations. So we'll use a lot more of this confidence intervals and hypothesis tests. That's mostly what the rest of the semester is going to be, different applications of it. Okay, that's it for today. I'll see you on the next set.